Okay.
Yeah.
It's better already, yes.
Yeah.
Do you see? Do you see it?
Yes, we see.
Yes. Yes, we see.
It's enough to,
Yeah.
or I can
So-
make it bigger.
Billy, you can rotate your iPad. Yeah, it's better.
Yeah. Yeah.
Then I can.
Okay, so we start. Our next speaker is Vladimir Roubtsov with the talk Multiplicative Bessel Kernels from additional laws to Calabi-Yau periods. Please, you can start.
Yeah, thank you very much. First of all, sorry for this delay. And second, of course, I'm very, very grateful for this invitation because I have special feelings to both guys who are reason of this interesting and fantastic in our condition conference. And I'm very happy to share with them my small observation. When I was young, very, very young, I liked Beatles very much. And of course, among their songs, there was a song which was When I'm 64. And I just never believe that it will be possible to have 64. Then 64 arrived, and I said, well, 64, and what's special for after? And because of many people, very good friends and very good colleagues who are elder than me, I understood that there is a life beyond 64 and even beyond 70. Very recently, I understood that there is a life beyond 70. Very, very recently. So I share with you, my friends, that the life is not stop at 60. You will have happy and joyful life beyond 60, and I hope beyond 70, 80. And as I wrote at the end of my talk, you have 60 plus 60, 120 to each of you, Leonia and Nikita. Scientifically, my talk will be a kind of disconnected set of facts, which we describe mainly due to old observation and old discovery of Maxim Kontsevich in our joint work in progress with Ilya Gaiur, who is here, and Duka van Straten from Mainz. At the moment, nothing is written, and there are many things are written. It means that there is no paper, but there are some pieces of this future possibly paper. And I was so much impressed with the beauty of the subject, which was proposed by Maxim in 2007. I was invited to discuss this subject 4 years later by Vasily Goloshev with Maxim, and then with Sasha Odesky, with Duko. Then we split it, partly invited other people like Anton Melit was also in this discussion. So my talk is, what's happened? My talk, it's about the following object of interest. It is a kernel. Here it is a kernel, which enters just in various products of solutions of interesting differential equations. Sometimes people call them motivic differential equations. Sometimes they are they have other names. So as I told you that it was raised in a paper of Maxim on 2007, and motivations which are split divided my talk on 4 parts, and I'm not sure that I will have time. So please, Misha, stop me 5 minutes before, because it's my typical error to lose time. So motivations are, first motivation, to find an analog of so-called Aperi-Baker-Zaghe list of second-order equations, which are important in arithmetic, in theory of zeta function values, in mirror symmetries, for higher order equations, like equations on periods of Calabi-Yau. Then the second motivation is so-called non-Abelian Abel theorem. This is a very homemade name given to our attempt to understand on the language of non-commutative operators classical Abelian, classical Abel theorem. Third motivation was recently became very, very popular. This is so-called analytic lengths of Kazhdan, Frenkel, and Ettinghoff. And the Hecke operators, which are real complex operators in their approach, they are motivated by a description of Hecke operators over in function field over finite fields given Maximin in his paper 2007. And my small part in this beautiful garden goes back to our paper with Benjamin Enriquez, where we describe algebraically non-commutative condition of integrability and quantization of so-called Bavil-Mukai systems. And this is nothing but a refined version of Skleanin separation of variables. Fantastically, in the case of multi-parameter kernels, which if I have time, I will describe, our approach can be helpful and useful as well. So the papers I mentioned in this motivation, it's a published paper of Ettinghoff, Frenkel, and Kazhdan, a preprint which is in archive with Vasily, Anton, and Duko, in the published paper of Maxim and Sasha Adesky in Letters of Mathematical Physics, and the paper with Ilya and Duko, which doesn't exist physically, but probably the proper name it Bessel kernels and beyond, geometry, combinatorics, and number theory. So that's what I want to discuss in my talk. The plan of my talk is quite ambitious. I'm not sure to follow it, but I will try. First, non-Abelian Abel theorem, then multiplication kernels for spectral problems. Then I will describe beauty of various Bessel type kernels, what we call experimental mathematics, because due to I would say fantastic capacity of computer computations of Ilya, we have many experiments and we have many results. We have no explanation of all of them. It is like yesterday Igor Krishever told that it is so, but I don't know why. By the way, one of our jubilars, Leonia, when we started to discuss many things, and I said, oh, it's beautiful, Leonia, why it is so? I don't know, said Leonia. It's so happened. So it's so happened. And the last, it's mentioned Skleanin, which probably I have no time to discuss. So first, a motivation comes from, as I told you, in attempts to find an analog of Aperi-Baker-Zaghe list. And in the case of higher degree, it concerns so-called Calabi-Yau differential operators, which are monic differential operators of the following type. Here, theta, as usual in this science, denote logarithmic derivation, and coefficients of this operator are degree n polynomials. And this operator, we suppose, should have so-called maximally unipotent monodromy at the origin T. How these operators appeared? They appeared in the following way. Let's consider a family of Calabi-Yau varieties of dimension n, and parameter T, and the family corresponding holomorphic differential top forms omega T on this family of varieties. Then the standard theory of Gauss-Manin gives that periods which are integrals over some R cycles on this Calabi-Yau satisfy certain differential equations, which are called Picard-Fuchs equation. The most known example, the most well-known examples of, well, I just, for your, maybe I save time and will not go into details, but to remind you that condition of maximally unipotent monodromy means that the monodromy matrix has only one single Jordan block with the same eigenvalues. So here it is just unity on diagonals and say 1, 1, 1 in the upper corner. And such condition guarantees that the basis of fundamental solutions can be written through the expressions with logarithm term everywhere except the zero term. So the first part of this solution, it is an analytic solution, phi zero, and other they have logarithmic more and more degree, and only last terms are analytic. So at the singular point with this condition, we have analytic solution. Anyway, examples, as I promised you. The first example of Calabi-Yau in dimension 1, it's elliptic curve. Here we just see, we can of course consider, for example, so-called Dwork construction of Picard-Fuchs equation, second order equation, which starts with standard Hesse cubic realization of elliptic curve in P2. But here it is a Legendre form with 0, 1, and t as a branch points, and period which is integral of the differential dx over square root of this cubic satisfy the following Picard-Fuchs equation. This is one example of this Calabi-Yau differential operator in dimension 1. Well, in dimension 2, there is, of course, many other interesting Picard-Fuchs equations and correspondingly Calabi-Yau operators. Here it is example of equation on a period of K3 surface given by Fermat quartic in P3. For trifolds with Hodge number H21 equal to 1, Picard-Fuchs equation and corresponding Calabi-Yau operator has order 4. For example, if we take Dwork quintic is a hyper surface in P4, then the Picard-Fuchs, one of Picard-Fuchs has this 4, which is similar to the Picard-Fuchs in dimension 2. Okay, then the second object, it is very, very classical. You know very well that multiplication theorems in Abelian approach are known as various addition theorems. But we can remind standard addition of logarithms, which corresponding to product of arguments. So it is just a group law in R star. We can also remind standard trigonometric addition theorem for sine, which in the language of arcsine also gives you algebraic expression for sum between x and y. And what is interesting, we will see, I hope I have time, that there is also, which goes back to Euler, elliptic addition law, which is, in fact, is given by so-called Landau transformation for elliptic functions used to compute Lemniscate arc lengths. And it is also have very interesting algebraic expression for this sum. Now, of course, everybody knows also addition theorem on the simplest abelian variety on the elliptic curve. This addition is modular given lattice, which defines this curve. The corresponding differential, it is this differential dx over y. Here it is in Weierstrass cubic form. And also we can interpret this addition like Abelian structure on zero Jacobian or zero Picard group using tensor multiplication of these shifts or classes, if you want, equivalent, linearly equivalent divisors. In a 19th century, Abel generalized this addition laws in very nice and useful way, namely using observations that for elliptic curve, instead of this group law, we can go to solution of corresponding differential equations with the form holomorphic one form, 1,0 form omega, and this solution is given by exponent of our integral. Then Abel theorem says that our addition can be written, of course, modular, again, modular lattices, as a product of this solution, and this product is naturally compatible with the exponential of sum. He considered hyperelliptic in modern language generalization of this fact, namely Abel considered rational differential R of xy dx and computed an integral of the form omega. And he proved that for any number n, there exists a number p such that for n bigger than p, you can reduce sum of n integrals to sum of p integrals, changing algebraically the limits, of course, modulo some elementary function, elementary or logarithmic or algebraic. And it gives possibility to multiplicatively reformulate Abel theorem for differential system on this Riemann surface X of genus G. if we have this system with this differential equation, then the product of solutions in n points can be expressed in terms of some kernel and product of solution in p point with the corresponding measure depending on the points y1, yp. And of course, this kernel, it is a kind of delta type kernel on the graph of this divisor relation in Jacobian. We will see this in trivial case. Our naive hope and our naive interpretation that we can go from Abelian case to non-Abelian, replacing line bundles and first order equation by vector bundles and nth order equation. It means that such multiplication formulas we can study for solution of this equation with lambda, which here can be interpreted not only like a spectral parameter, but more likely like an accessory parameter, which means that the local monodromy of this equation is independent on lambda. So our desired formula for solutions should have, as I mentioned in my introduction, the following way, where the solutions are polynomials with polynomial coefficients in this parameter lambda. So as examples of such equations and such kernels, I will describe in more details, of course, this so-called Bessel kernel type, because I warned you that I'm quite imprecise in my talk. It's a kind of superficial talk. I will call equation and function, say Bessel equation, Bessel function. In fact, it is Bessel type and Bessel type function. It is not exactly, they can be obtained by easy transformation. Maybe I will have a time to even to write this transformation from usual Bessel of zero kind to the form which I'm using for simplicity. But product of this simplified Bessel, zero kind Bessel, gives by so-called Sonin-Gegenbauer formula. This is also 19th century beautiful formula. And the kernel has algebraic form, and this algebraic form is extremely beautiful, and you can find it in old handbook of Naum Yakovlevich Vilenkin about harmonic analysis and representation theory. And this function SYZ is nothing but so-called Heron triangle error function. Then D2 equation, which is a special, also special kind of differential equations, which people in number theory likes very much, and then mirror symmetry. This is so-called small a priori operator, small a priori. It is operator of second order, which depends on cubic polynomial f of t, t3 plus a t2 plus t with a zero free term. Then the corresponding multiplicative kernel is also algebraic, and you have closely related to this Heron expression polynomial in 3 variables, which is discriminant of quadratic trinom, which you obtained if you consider the difference between this a priori cubic t2, 3, and etc. Minus factorized cubic with x, y, z like roots. Then you have a second order expression, and the discriminant of this expression gives you 3 variable polynomial, which is a special kind, so-called Kontsevich polynomial. Kontsevich considered his polynomial, as I told you, in function field over finite field characteristic P, and he used it to compute a number of so-called Hecke operators in the point of this field. And this is what I don't want and no time to discuss. Now, his approach, I mean, approach of Maxim, which was beautifully realized with Sasha Odesky, considered the kernel computations is a kind of computation of structure constant. Of course, it is very naturally to think even in finite dimensional case and in functional case, it is just a convolution with delta function kernel. But the main technical result of Odesky and Kontsevich is the following. Let's consider a set of polynomials. P0, P1, and etc. Each polynomial Pi has degree I. Then one can introduce the structure constant tensor C of ijk, that the product of ith polynomial, jth polynomial gives you the kth polynomial as a series or summing by k. So how to compute this? One can consider generating function with coefficients given by these polynomials, ith coefficients, Pi's polynomial. And we denote this function by f sub lambda. Then Odesky and Kontsevich introduced one form kernel depending on x, y, and dz over z in some degree, in some power, and proved that there is a kernel, multiplicative kernel formula of this one form applying to f lambda, my series, generating series in Z. It gives you product of series in X and Y. The integral, of course, you can think about like a residual corresponding series. It is very important that lambda here, it is not only a single possible parameter. You can consider multiple parametric generalization, and this multiparametric generalization also were considered, generalizations were considered in the paper of Maxim and Sasha. Our approach was quite naive, and we call it master formula. Maybe it is master formula, it is means almost nothing. There is a master equation, master relations. So we call it master formula because we liked the simplicity, how it works in some toy models. So let's consider for some differential operator L sub x spectral problem with accessory and spectral parameter lambda. This master formula, which I will describe, works perfectly for second order differential operators, what corresponding JL2 matrix case. And also, and everywhere, we will suppose that our equations, they have an analytic solution at origin. So, or maximally unipotent monotony. Then the master formula, it is just a naive observation that if we have this spectral problem in Y with the eigenvalue lambda and eigenfunction phi 0 of lambda Y, then we can put and we consider that just a solution as a generating series with polynomials p sub I in lambda like before, and each polynomial i's polynomial has degree I. Then, taking the corresponding spectral problem for operator pi of lambda in Y, applying to my eigenfunctions, we obtain the same eigenfunction, but with eigenvalue pi of lambda. And this is true for our master formula. This observation is so we can try to take the product, say action of operator, put operator lambda instead of lambda in F0, applying this operator to F0 lambda Y, and then we obtain that F0 lambda Y is the eigenfunction with eigenvalues F0 lambda X. So you have in right-hand side the product, and here you have action of operator to one of these. And this master formula, it was happened that I think it is a beautiful observation of Vasily Golyshev, and beautifully used, Ilya used this observation. You can use it in purely linear algebraic, but computer procedure, how to recover series for this kernel. Now, I will not discuss it. If you want, you can details of this computer. It is very nice packages and very nice computer algebra, but it gives fantastic answers, and you can try to understand and interpret these answers. So let's consider our master formula in the toy model case. So let's consider so-called one Bessel operator, or it's better to say one Bessel type operator in dimension 1. It is just the operator theta, which is logarithmic derivative, like I told you, and corresponding spectral problem for this theta. Then normalized solution of this is just exponent lambda to lambda x. Consider the corresponding series. Then a multiplication formula between two exponents, of course, gives you exponent of sum and can be represented in integral form with delta function kernel. Or you can interpret it with the help of Cauchy type formula as integral over small circle on Z around the X plus Y. So if we apply our approach, our master formula, then we also obtain the same answer. And this is, you can get in some handy way, not only by computer, but in some handy way, if you use the observation how we apply derivation in the case of Cauchy formula, how we can apply operator of multiplication, like in Fourier transformational, Laplace transformation science. We can interpret it like integral form operations. And
Vladimir, sorry, we have 5 minutes left.
5 minutes, okay. So this conceptually, we can get the same answer from master formula using this series and but substitution of D. Okay, now it's time to show some 5 minutes to show some beauty. First beauty, it is so-called Sonin-Gegenbauer formula for n equal to 2 Bessel type operator. You remember I told you about this function S, which is in fact in this case has a very nice polynomial, quadratic polynomial, fully symmetric in X, Y, and Z. And using computer package generating function, you can get this answer not only like a multiplication of Bessel function, but also from this master formula solution. And one can consider generalization of this. Namely, we can consider n degree analog of Bessel, so the operator x d over dx in degree n, and the solution which I, of course, ambiguously called nth Bessel function, but it is this series in x with the coefficients lambda to k over k factorial in degree n. And taking parameter lambda equal to 1, the product of such solutions gives you the following expression. It is just elementary computation. Dividing by z to m plus 1 and multiplying with the function in z, we have the following kernel formula with the help of this generating function in two variables. This generating function in two variables absolutely fantastic. If you have n equal to 2, then this algebraic kernel, it is 1 over square root of delta, which depend on x, y, and 1. So you can interpret x, y, and z like coordinates, homogeneous coordinates in P2, and big x, y like corresponding affine coordinates. And then the quadric, which I showed you, defines a configuration of a circle which tangent to 3 coordinate lines in P2 with the equation x, y, z equal to 0 in the midpoints. And after substitution x, y, z by squares, you have a factorization, which factorization is here on configuration. You see half a perimeter and half perimeter minus 1, minus 1, minus 1 length. So this product is 16 times the square root of triangle with this u, v, and w lines. So this is a n equal to 2. For n equal to 4 and 3, you have similar but much more complicated expression. For example, you have always hypergeometric function enters in your kernels, and the singularity locus instead of quadric now became cubic. And we have a conjecture which we have serious reasons to consider like true, that singular locus of d module of degree n corresponding to this n Bessel, it is always contains coordinate triangle x, y, z equal to 0, and rational curve of degree n, which has n minus 1 and minus 2 over 2 double points. And this curve intersects coordinate triangle only in 3 midpoints. And we have the symmetric polynomial delta x, y, z, which starts with x to n, y to n, z to n. And it completely determines by the property that if we replace x, y, z by nth degree, then we have a factorization with using nth root of unity. And these configurations, they are, first of all, they are partial case of Kontsevich polynomials, which he introduced in 2007. I also have time to say one word that recently, maybe 4 years ago, Fernando Rodriguez Villegas with Danilo Radchenko, they published interesting combinatorial paper about so-called Horn hypergeometric graph. And these configurations also appears naturally in their combinatorial approach. I have probably 1 minute to say about how this Kontsevich generalized polynomials and our special cases are related to so-called two-valued formal group laws. I will have no time to remind it, but people should know about it. And I just say that Viktor Matveyevich Buchshtaber in 1990 gave, based on their joint paper, previous paper with Novikov, gave a description of so-called two formal group with multiplication law defined by the quadratic relation. This group they called square modulus of original formal group. So this multiplication law gives by polynomial also in three variables z, x, and y, given in very special form. So if we take our delta Bessel n equal to 2, we explicitly find the Buchshtaber polynomial group law for homologies. This is the first example which was discovered by Buchshtaber and Novikov in 1971. Later, Buchshtaber, Mishenko, and Novikov proposed the similar law for formal group in K theory with a parameter Q, which goes back to both periodicity. So it is a U plus V minus Q UV. And then this Buchshtaber family gives you nodal Cayley cubic in P3, if you want to consider this. This is a fine, of course, a fine cubic, a fine part of this Cayley nodal cubic. But the most interesting, of course, it's a elliptic formal law. In Buchshtaber classification, such polynomials which gives elliptic law also appear for special value of parameters. They depend on three parameters, and this parameter depends on point alpha on the given elliptic curve. So for a special choice of this point, namely if it is a zero of P function and other A2 and A3, they are coefficients G2 and G3 in the equations of equation of elliptic function, Buchshtaber and Veselov show that there is a transformation of Buchshtaber polynomial, and this transformation can be reduced to additional law, very simple additional law for P function by this beautiful change of variables. And this is because of so-called Burnside addition discriminant, which he published in Messenger in 1873. If you look this discriminant, you exactly obtain one of Kontsevich polynomials. And the zero locus of this polynomial is K3 quartic in P3 with 6 singularities type of A1 and 3 singularities of type D4. I stop here because unfortunately I have no time to say about beautiful numerology, beautiful integer sequences which relate to these kernels, and how we discovered by eyes for two Bessel palindromic property and generalization of Pascal triangle of squares of integers, and then relation with Narayana and Catalan numbers. So you can also check that interesting relation which we discovered can be found also in the famous site of integer sequences for both Bessel n equal to 3 and equal to 4. Okay, thank you.
Thank you. So I remind that the next talk will be at 4:10, so we have a 5 minutes break. And I suggest that if someone have any question, please feel free to ask and discuss everything you want in a free form.
I believe Vladimir wants to show the last slide.
Of course, the last slide. I want to show. Ой-ой-ой.
Почему-то у меня другой он.
Yes, of course. I don't know why. Okay, I can stop this and I can show another. I can show the last slide.